EET 114, Chapter 25 continued. So we have transient RC networks. What is that? Well, you guys know what an RC network is. It's just a resistor in series with a capacitor. So this formula should look very familiar. This is the voltage across the capacitor, and this is the generalized equation. It's the final voltage plus the quantity of the initial voltage minus the final voltage times e to the minus t divided by RC, which is tau, if you remember that. Tau equals RC. So VC is the discharging voltage in volts. E, big E, is the DC source voltage in volts. T is the time. It's an independent variable in seconds. Tau is the time constant tau, and it's equal to RC for this case, R times C. And then resistance is in ohms, capacitance is in farads. Little e is a natural number, e to the x button on the calculator. So then we have this equation also. Covered this up a little bit here. This should be tau, not big T, it's tau, which I think is actually Greek for little t. Yeah, there it is. So I sub c is the charging current, and you guys have seen this equation before, in amps. And VR is the voltage across the resistor during charging, in volts. And then VC, this equation is the same as this equation up here. VI is the capacitor initial voltage value in volts. VF is the capacitor final voltage value in volts for the charging phase. If VI equals 0, if you make VI equal to 0, then this equation turns into this equation. All right. So this is a square wave right here. This would be the input wave. Looks like this. This would be a DC value. Right in this wave, the DC value is 0. And then in this wave, it's something higher than 0. It just shifted the whole thing upward. So this is what an RC network looks like. So you'd be applying this input voltage to this RC network, and you get an output voltage VC. So whenever you do that, if you get if V, this is V and C, VC IC for the period divided by 2 that's greater than 5 tau. If it's greater than 5 tau, it gives it time to charge up and it flattens out right here, okay? And then whenever it discharges, this is the charging phase, this is the discharging phase, and then so on. It keeps repeating. The current starts off high because the capacitor starts off as a short, trails down to 0 because it ends up being open, and then it goes in the negative direction, and it keeps doing that. These two go together. If T over 2 is equal to 5 tau, then it just barely has enough time to discharge. Right at the T over 2 moment, it peaks out and then it discharges. So then it looks like that. So this looks like a flattened shark fin. This looks like a perfect shark fin. And then these pulses are a little bit longer here with the current. And then likewise, if T over 2 is less than 5 tau, then it doesn't have enough time to charge up. Okay? And it looks like a little bit flatter, more like waves on the ocean. And likewise, this doesn't have fully time to discharge and for the current to go to 0 before it goes to the next pulse. All right. So under steady state conditions, the average value of VC will equal the average value of the applied square wave. And we are not going to cover oscilloscope attenuator and compensating probe. And that's it for chapter 25.